Okay, we're live. Let's see. I've got a little bit of background noise. Nikita, can I ask you to mute the microphone for now? Thanks. Okay, so I'm going to go through what's called this method. This is another way of creating three-dimensional shapes using volume. So let me do a video representation actually before I get started. So I don't want you to worry about the shell method on the right-hand side. I'm just going to focus on the dis method on the left-hand side for this. So what we're doing with this dis method.
Mr. Brennan, the screen is not showing
Oh,
on Zoom.
screen's not showing on Zoom. Okay. Okay, I forgot to share it. Can you see now?
Yes.
Cool. So I'm focusing on this dis method on the left-hand side. We use dis method typically when we're evolving around a horizontal axis of rotation. So in this case,
Some of them are cut from the.
okay. See how close I can get. Okay, I realize I'm cutting off just the top part where this says dis method, but I think that's about as close as I can get.
Is there anything on the left side that the formula has?
Can you see pi times the integral of a to b?
Yes.
Okay, that's as far left as it goes.
Okay.
Okay, cool. So back into this. So we use dis method whenever we're evolving around a a horizontal axis of rotation. So in this case, the x-axis. And what we're going to do is we're going to create a bunch of vertical disks that spin around that axis of rotation. For today, we'll just be doing one disk at a time, an outer disk, so our shape will be solid, not hollow like this one that I'm building right now. But if I wanted to cut a second smaller disk out from that disk, then I could create a hollow shape. So we'll take that two-dimensional disk, that's a 2D area, and we'll spin that 2D area around our axis of rotation to create a three-dimensional shape. So in the end, here's our 3D shape once we've done our integration about our axis of rotation. Gives us this weird donut-like shape. In American football, we've got a thing that we put on the ground that looks just like this in order to hold the football when you want to kick it. Is what I think of in my head, but okay. So let me walk through an example. So here I've got a shape that I want to revolve. I want to spin about the x-axis. If I took this two-dimensional shape and spun it around the x-axis, I would end up with a shape that's almost like a bullet or an acorn. So what we're doing is I'm taking a radius, so that's my distance from the axis to the outermost function, which in this case is our y value. And I'm using that radius as the radius of a circle to create a two-dimensional circle, which would have volume if I made it three-dimensional with this infinitely small depth. And then just like the last class, I'm going to stack those on top of each other infinitely many times to create our shape. So each of these 2D cross sections of our acorn or bullet shape will end up adding together to build on top of each other to create a smooth shape like this as a solid. Okay, any questions on the concept? So general idea of what we're doing.
No.
Okay. So for our first example, I usually start by drawing a box. So I've got our radius is my distance from the axis of rotation to our outermost function. Distance from the axis of rotation to the outermost function, which in this case is our y value minus 0, since I'm spinning around y equals 0. Okay, so I've got my y value up top, and then down here is y equals 0. The difference between them would be y. Okay, so my radius is y, then I can use that to create a disk, which would look like this. That we will spin about our axis of rotation. So if I use the same color as last time, then I have an infinitely small depth to that disk that I'm spinning about the axis. So from here to here is dx. Okay, and then on the inside here in yellow is our two-dimensional cross-section. With our radius shown in red. Okay, so we're going to keep stacking these disks on top of each other until we create this three-dimensional acorn-like shape. Okay, so our radius is our y value. I'm going to use that to make my two-dimensional area here of the yellow part. So that means my area is, since this is a circle, pi r squared. Rewrite right here. I know I'm writing the same thing, but area is pi r squared. Is pi times y squared, since my radius is y. Which we drew in red for our picture, so I'm going to throw that here. R equals y. Okay, then to make it a volume, I would have to multiply by dx. So my volume, I could say, is equal to the integral from our start point to end point, which in our case is from 0 to 4 of pi times our radius, which we said was y squared times dx. Okay, pi is a constant, so I can move that out. And then we've got an equation for our y in terms of x. We were told y is equal to square root x. So we can substitute that in. Our volume is equal to pi times the integral from 0 to 4 of the square root of x squared in terms of x.
Mr. Brendan,
Yes.
is it like the limit, the highest value, is it because it's 2 squared, so it's 4?
Highest value here is actually our ending x value. Since I'm integrating in terms of x, we know that because we've got a dx inside our integral. Then I need a starting x value and an ending x value, which for us is x equals 0 and x equals 4.
Okay.
But they could have set that cutoff point anywhere they wanted.
Okay. Thank you.
No problem. Okay, so now I've got an integral, and we're all in terms of x. So because it's all one variable, we can integrate. I'm going to jump over to start calling on people now. So let's see, I just heard from Abby, so let me jump over to Andrew. Can you help me with
Yes.
this integral?
Okay. So root x to the second power will be just x, and that x will be, if I integral that x, it will be x squared over 2.
Okay, and that's a constant on the outside, so I'm just going to multiply that in. So this is pi times x squared over 2. I would have plus c, except I've got bounds, so what do I do with my bounds?
So upper bound minus lower bound, so pi 4 squared over 2 minus pi 0 squared over 2, which is 0.
Perfect. I guess I will plug that in just for the notes. Okay, so what's our final answer?
Will be 8 pi.
8 pi, perfect. It's the volume of our acorn or bullet that we created by spinning this radius about our axis of rotation. Any questions on what we did? Whoa, too much. Okay. I'm going to take our same example, and this time I want to be able to create a hollow shape. So instead of spinning around y equals 0, I'm going to take this function here in blue, which was y equals the square root of x. And we'll still stick from x equals 0 until x equals 4. But this time I want to spin around the line y equals -4 to create a three-dimensional shape. So I would write something like find the volume of the solid formed by revolving the area, bounded by y equals the square root of x. The x-axis and x equals 4. About the line y equals -4. Give myself a little bit more space. Okay, so what we're going to do is almost the same thing as last time. I'm going to create... I should have color-coded this axis differently because I used red for the radius last time, but oh well. I'm going to create our radius in green. So I'll pick somewhere in the middle here. My first radius is going to be my distance. It's going to get messy. R1 is the distance from the axis of rotation at y equals -4 in our case, to the outermost function. Which means the function is the furthest away from the axis. Okay, give this a little bit of depth too. just a little bit. So that's a little bit rough to see. And then also let us see the part of this I want to cut out, which will be here in, we'll do orange. In orange, I'm also going to cut out a smaller radius here, which I'm going to call R2. R2 is the distance from the axis of rotation at y equals -4 in our case, to the innermost function. Innermost meaning the closest. So I'm going to use both of these radii to create disks. Okay, my first disk here in green would look like this after I spin it. And then my second disk here in orange would look like this after we spin it. Okay, again, we've got depth to these, which is an infinitely small depth we can represent as our change in x. So what we're really doing is I'm taking the area of one large disk and I'm cutting out the area of one smaller disk from it. So I'm going to do this in a slightly lighter green so I can still see my radius there. One large disk. Whew, this is a lot to shade in. And one smaller disk that we're cutting out of it. Good enough that it doesn't look see-through. Okay, then all right, quite a lot going on in my picture, but redraw my outer radius here so you can see where that's going from. Our outer radius goes here. All right. Any questions on what we're doing? No, I've got quite a bit going on in my picture.
Why is there -4 again?
So this -4 is the axis of rotation that we're going to spin around. So instead of spinning around just the x-axis at y equals 0, I want to take this shape and spin it around a line that's a little bit further down. So if I do that, when I go to construct this acorn or bullet-like shape, I'm going to end up with a circular hole that goes all the way through the shape. So instead of I'm not trying. Instead of a three-dimensional shape that looks like this, where we spun around an axis of rotation, I'm going to end up with a 3D shape that's hollow. So it would look like this. We had the green part, which was our large disk that we spun around our axis of rotation. And then I cut out the yellow part, our smaller disk, from it. Just going to draw this as a line. This is my axis, and it goes all the way through the shape. And I use that to spin this around and create this three-dimensional acorn-like shape that I have drawn here. Okay, I'm really bad at coloring, but do you guys understand what's going on? Abby, are you okay?
Yes.
So we just create another circle inside of a circle in order to make it hollow?
Yes. We're cutting out a smaller disk from the large disk, and that will make it hollow. In this case, we're cutting out a perfect cylinder because it's all the inside part never changes. This inside radius here in orange is always going to be 4 units long, right? Distance between y equals 0 and y equals -4 is always 4. But our outer radius in green is our distance between y equals -4 and y equals square root x is going to be root x plus 4. The square root x that gets us to 0 plus another 4 units to get us to y equals -4. So I'll end up with like a hollow circle that's always the same circle in radius all the way through our acorn shape. Okay, so math would look like this. First we've got R1 is my distance from my axis to the outermost function here in blue, so that's from the orange axis here to the blue line, is the square root of x plus 4. R2 here in orange is my distance from the innermost function, which is here in black, the x-axis, to the axis of rotation, which is -4. So my difference between 0 and -4 is 4 units. My volume then. Oh, I guess I'll do area first. My areas, since we've got 2 of them, are pi r1 squared and pi r2 squared, which in this case would be pi times root x plus 4 squared. And pi times 4 squared. Everyone okay so far?
Yeah.
Okay, then my total volume then of this shape would be what happens when I multiply these areas times their infinitely small change in x. Or I could say our total volume is equal to pi times the integral of your start point to your end point of r1 squared minus r2 squared times dx. Now I've done quite a bit here all in one step. This is actually my general form that will work for any function you want to create of a hollow shape when you're spinning around a horizontal axis of rotation. But if you multiplied all of this out, this would be pi times r1 squared is a1 times dx makes it a three-dimensional volume. Minus, if I distribute, pi times r2 squared is a2 times dx makes it a three-dimensional volume. Okay, so for us, this would be volume equals pi times the integral from our start point at x equals 0 to our end point at x equals 4 of r1 root x plus 4 squared minus r2 4 squared times dx. And that dx is actually being multiplied by everything. If you don't write these parentheses, that's okay. They will assume that you're multiplying dx by everything as long as you've got an integral sign. So you don't have to write these, but I'm going to do it for now just to point out that you are actually multiplying this by everything that's inside the integral. Since integration is still a little bit new for us. Any questions on our setup? All right, let's finish this one out. So I'm going to integrate the rest of this, and we are over to Eric next. Okay, Eric, what's going to happen when I square this?
X plus 16 minus 16. 0. Yeah.
I need one more term here, I think.
Yeah, right.
Okay, the minus 16 we got from the other side. Okay, so what's my middle term, though?
8 x.
8 root x, okay? So that leaves me with my volume is equal to pi times the integral from 0 to 4 of x plus 8 times x to the 1/2 power is the square root. And my 16 and 16 will cancel. So what happens when I integrate this?
X square over 2. Eight x 3 over 2. And also 3 over 2.
Perfect. If I'm dividing by a fraction, we'll flip and multiply. So before I plug in my bounds, we'll do that. If I flip this and multiply, what will this term become in front of the x to the 3/2 power?
2 times 2 over
Times 2 over 3. So that'll be 16 thirds x to the 3 halves power. Okay, so I've got pi x squared over 2 plus 16 to the 3 halves over 3 from 0 to 4. It's just a question. You don't, because we've got an option here, but would you guys leave this as x to the 3 halves power, or would you rewrite this back into a root form?
Leave it.
Leave it? Okay, cool. So I'll leave it then. If you did want to rewrite this in root form, then this would be x cubed under the square root. Or you could say x root x. Since if you've got two x's on the inside, you can pull them out. I guess I'll write that rule over here too. So x to the m over n power is the same thing as the nth root of x to the m power. Okay, so last step, I need to plug these in. I'm going to jump over to Niall for this, since I've called on Eric a lot. Niall, what happens when I plug in our upper bound minus lower bound?
Wait, can you say it again?
Yep, I want to plug in the upper bound minus lower bound to finish this one off.
Oh. Um. So, first of all,
I think he just dropped. Yeah, I'm pretty sure he just dropped. Okay. I'm going to jump over to someone on Skype then. Let's go. I've got top of the order for Nini. Nini, what's going to happen if I do upper bound minus lower bound here? Okay, no microphone so far. Next would be Kyle.
So do we just input 4? So pi 4 squared over 2 plus 16 4 to the power of 3 over 2 over 3.
Okay, that's good. 16 4 to the 3 halves power over 2. Okay, this 4 to the 3 halves power is the square root of 4 cubed. What's the square root of 4?
oh, sorry, I got disconnected.
Square 2.
Okay, that's okay. So square root of 4 is 2, and then 2 cubed is 8. So this is 16 pi over 2 plus 16. Hold on, I don't think I multiplied by pi, did I? I did not. It should be 16 pi. 16 pi, there we go. 16 pi, and then we said 4, the square root of 4 is 2. 2 cubed is 8, so this is 8 over 2. Everything's over 2, so since we already have a common denominator, I can combine these. Or I could just divide by 2. I'm just going to divide by 2. So this is 8 pi plus the 16 divided by 2 is 8 times 8 is 64. 64 pi. Gives me
72.
72 pi. Any questions on our volume?
Nope.
No.
Wait, but next time we do our homework, for interior circle, do we always just plug in its radius, nothing else?
Yes,
Like
because
just the number, no formula?
our area is pi r squared. So even though this formula only shows the radius inside the integral, we're really multiplying this radius squared times pi. So this is really a1, our area one, minus a2. I've just simplified a bit for our formula.
Okay.
Okay. Any other questions on this one?
No.
Okay. Let's see. We are 45 minutes in. Do you guys feel like we need one more example, or do you think we're okay?
One more.
One more. Okay.
Yeah, let's go through one more.
I'm gonna see if I can make this a little harder, maybe. So I'm gonna generate one that's worse than anything that's on your homework, but we'll do a shifted x, and not gonna let me do a shifted x for any trigonometric function. Okay, we're gonna have to make it harder. Bah. Alright, I'm just gonna make one up, because I don't really like what I'm generating. I'm gonna say we've got a sine function and a cosine function. Maybe redraw that. Actually, can I cheat? Ha. Okay. So this is y2 is cosine, and y1 is sine. And I want to take the area in this region, which we'll call region R. Rats. Okay, I'm going to take the area in this region, which I'm going to call region R. And I want to spin that about the line y equals -3. Here in pink. Okay, so if I spin this, about our axis of rotation. I'll end up with something like this. After we spin.
Will we have this in our homework?
Your homework's a little bit easier than this, but after the next class we will. It's sort of all the stuff that's hard about all of your homework problems, but in one problem, if that makes sense. All right. So what I've done is I've spun this area about our axis of rotation. If I spun this area about our axis of rotation, I would end up with a 3D shape after spinning that looks something like this. Actually, let's just use the machine for this. So a 3D shape that looks something like this. So after I spin it around, it'll end up looking like this shape in 3D. Okay, any questions on what we're doing so far? Okay. So I'm going to take this top half before we spun it. And we'll copy that over into our Word document. All right, so I'm going to pick a point in here and we'll create our radius the same way we did last time. So I'm going to have in green our R1. So somewhere here in the middle. My R1 is going to be my distance from my axis of rotation to the outermost function. And then my R2 here in orange would be my distance from the innermost function to the axis of rotation. So in this case, that would be R2 would be the difference in my y values of cosine x and -3. Or cosine x minus -3, which is cosine x plus 3. My R1 would be my difference in my y values of this black function and the pink function, which would be y1 is sine x minus our axis of rotation is at -3. So sine x minus -3. R1 would be sine x plus 3. Okay, is everyone okay with the radii that we picked so far?
Is there an equation for this?
Wait, just to clarify, why did we pick them exactly in that position, not a different one?
Doesn't matter which position you pick, this will still be true. So if I picked somewhere over here, then this would be R1, which is still the distance from the pink function to the black function, sine to y equals -3. And my orange would be here. For R2 is still the difference between the red function, cosine and -3, which would be cosine minus -3 is cosine plus 3. So it doesn't matter where you pick, our formula is still the same. Abby, you had a question, but I think it was cut off.
Is there a specific equation for this question? Or is this just like y2 equals cosine x?
So we were given these two equations. Y1 is sine, y2 is cosine. If you want me to write out a question, I can. So let's say, to wrap this behind text, I think, for this to work. My question would be something like, find the volume for the solid resulting from rotating the area between y equals cosine x and y equals sine x. From their first intersection in quadrant 1 to their second intersection in quadrant 1 about the line y equals -3. Okay, I'm going to shrink our text just a little bit so that I don't run into that. Y squared equals cosine x. Okay, so my goal is to spin this area R, about the pink line, y equals -3, in order to create this three-dimensional shape that I'm kind of showing the bounds of here. So if I wanted to draw this out in 3D again, it would look something like this. I've got a green disk that I'm going to spin about our axis of rotation. Like that. With an infinitely small change in x. And then out of that green disk, I'm going to cut this orange disk. Again, with an infinitely small axis of rotation out of the middle. So something like this. Let's go all the way up to that line. Okay. Any questions on what we're doing?
Mm.
Redraw my radii on the outside here.
Oh,
so
wait,
it's-
why?
Say again?
Oh, never mind, I figured it out.
Okay. R1 from here to here. Okay. So I've got R1 is my distance from the axis of rotation. The pink line to the outermost function in black is top minus bottom. So that's sine minus -3 is sine plus 3. R2 is my distance from the innermost function. So that's the one that's closest to the axis of rotation. So again, difference in the y values would be cosine minus -3 or cosine plus 3. Okay, then we can make them areas. So A1 would be pi r1 squared, and A2 would be pi r2 squared. Our volume would be A1 minus A2 times dx. Or pi times the integral from our start point to end point, which we'll get to in a second, of our r1 squared minus our r2 squared times dx. That's pi r1 squared times dx is my volume for the green shaded region. Pi times r2 squared dx is our volume for the orange shaded region. Which I guess I'll color code. So r1 squared and r2 squared. Okay, so I do need an a and b now. So that's my start point and end point for this. And I'm going to have a and b whenever these functions cross. So that's whenever the sine is equal to the cosine. Well, if sine equals cosine, then sine divided by cosine should equal 1, divided both sides by cosine. And the sine over cosine is the tangent. So whenever the tangent equals 1, sine will equal cosine, which happens at 45 degrees, pi fourths. And then again at 5 pi fourths. On our unit circle, that's here and here. Where x and y are root 2 over 2 and root 2 over 2. And in this case, x and y are negative root 2 over 2 and negative root 2 over 2. So that's my a and b. R1 sine x plus 3 squared minus R2 cosine x plus 3 squared times dx. Okay, any questions on our setup for the volume?
No.
Okay, so last part we need to integrate. Who are we on? I'm on Nikita over on Skype. So I'm gonna have you expand with me, and then I'll help you. I think we'll probably stop there after we expand, actually. So I don't know that we know how to integrate all of this just yet.
So do I just plug in the numbers, the values?
So for now, help me expand this part. So what happens when I square sine x plus 3?
Just checking. I don't remember what sine squared.
That's okay. So sine squared.
Oh, just sine squared? Okay, then I guess sine squared x plus 9
Okay, we've got a middle term as well.
plus, yeah. 2 sine x plus 3.
Two sine
Um,
x times 3. So that would be
6 sine x
6 sine x. Perfect. Minus.
minus cosine x squared
Okay.
plus 6 cosine x plus 9.
Plus 9. Okay. Unfortunately, for this class, I think we're stuck at this point. Since sine squared minus cosine squared isn't a value that I can substitute in for with our trigonometric identities yet. And we don't know what we don't know how to integrate that yet. So at this point is about as far as we can go. Oops, I've got my pi on the outside here too. Pi. I could throw this in a calculator if we want. This is what I get for picking a problem off my top of my head instead of using the program, I guess. But so I'm gonna plug in R1 as Y1 and R2 as Y2. So this is sine x plus 3. Oops, sine x, close that, plus 3. And this will be the cosine of x plus 3. So I've got R1 and R2, which I'll sub in for here. Second quit. I'm going to go to math, and my ninth option down is integrate. Takes 4 arguments. Your first is your equation, so I'm going to type in all of this. Your variable, in terms of x, from your lower bound to your upper bound. Okay, so I've got variables, functions, y1 squared minus variables, functions, y2 squared, which I want to integrate in terms of x from x equals pi fourths to x equals 5 pi fourths. Double check and make sure I'm in radians. Yep, before I run this. Okay, so that integrates all of this part for us. Is 16.97, and then I have to multiply by pi to get our final answer for the volume. So this is what would happen if I spun this shape about y equals -3, I would end up with this much space full of volume. And my shape would end up being a hollow shape that looks kind of like a flower almost, or the leaves of a flower. Kind of opening up if you looked at it from the top down. Any questions on what we did?
No.
Okay. So I'm going to stop there for today. You don't have anything on your homework that is quite this difficult. I was trying to throw kind of everything into one problem and didn't work out very well because I ended up with something we don't know how to integrate yet. So the homework is easier than this last one. But the process is the same, where you're still going to be looking for an R1 and R2, and ultimately plugging into this equation for disk method.
That's real.
Thanks, you too.
What is the homework due?
So this one will be due on Friday for you guys.
Friday at 9?
Friday at midnight.
Oh, yeah, okay.
I'll zoom into this in a second. Need bounds. There we go. That's not the right integral. Need this one. All right, so general form if we need it. Ultimately, we'll be doing this for pretty much every problem. Keep that a lowercase b. And what this is doing is taking an area 1 as a disk, as a circle, so pi r1 squared, and then subtracting a second area, pi r2 squared if you distribute, times our dx makes it a volume, a three-dimensional shape, where that dx is an infinitely small depth to each of these two-dimensional disks that I'm subtracting one from the other. I'm cutting one disk out of another disk. For your homework today, there will be no innermost disk. So everything is just going to the x-axis, I believe, for the homework today. For your homework for Friday, all of your questions will have an innermost disk, which means you won't be going to the axis y equals 0. Your axis will be anywhere else. Okay, any last questions before we break?
No.
Cool. I'm going to post this to the chat really quick. Thank you very much for coming. We are well over time, actually. I apologize. I will see you on Friday.
Thank you. Bye.
Bye.
Good.
Mr. Brennan, can you
Thank you.
Uh,